This meeting is being recorded.
In this next section, 17.4, we're going to review benzene and specifically benzene stability. So aromatic rings in general are remarkably stable. We'll begin with benzene and then expand to other aromatic compounds. We should compare, though, first that alkenes, which have only one double bond, so that's what we see here in this cyclic alkene, readily will undergo addition reactions. So here we have added molecular bromine across the pi bond in this fashion here. So we can see the stereochemistry represented in our product. But if we were to try and react an aromatic ring, such as benzene down here, with that same reagent, with Br2, there would be no reaction. So why is this the case? Benzene, we know through an analysis of what we refer to the heat of hydration, is much more stable than would be predicted if we were to compare it to an alkene with a single bond shown here, a diene shown here, and then up top here would be the expected energy that would be contributed from this structure here, a benzene ring. But the actual structure is much more stable and at a much lower energy that we see here. So if you recall, the heats of hydrogenation, this is in reference to if we were to hydrogenate these compounds using either 1, 2, or 3 moles of H2 gas to fully reduce these compounds, they would all reach this energy down here, and the most stable form of cyclohexane, the chair conformation. So that's what we see, all of these either single double bonds, two double bonds, or triple double bonds, resulting in the same product. So that's how we can compare the relative stability of these compounds, the energy difference between each of them to reach the fully reduced form of cyclohexane. So again, what we observe with benzene is that it exists in a much lower energy state than will be expected. So molecular orbital theory, as mentioned previously, can help us to explain this aromatic stability. If you recall, 6 atomic p orbitals will make up, and we see that over here, 6 molecular orbitals. And this orientation is seen over here, where we have our lowest energy molecular orbital, our second highest, shown here at this level here. So we have 3 bonding molecular orbitals below this line here, and then we have our anti-bonding higher energy molecular orbitals above. So the location of a node or a site of 0 electron probability is contributing to the energy of each of these molecular orbitals. And you will not need to know any of the mathematical calculations that are referenced here to determine the actual shape of these molecular orbitals. But because of these molecular orbitals, we see delocalization of these 6 pi electrons in these 3 bonding molecular orbitals, and that is what accounts for this stability of benzene. Again, that delocalization of those electrons. So we can see here that not all fully conjugated rings will have aromatic stability. And these here, both cyclobutadiene and cyclooctatetrene, both would be considered fully conjugated rings because we have these alternating single or sigma bonds and pi bonds. Because we can see that they would still react like normal alkenes. So that's what we see here with the cyclooctatetraene. This will react just like a regular alkene, and we could brominate one of those pi bonds. Also, aromatic stability is not seen with this cyclobutadiene structure here. It is actually so reactive that it will react with itself and form this structure over here, again, a cyclooctatetrene. So we'll continue with part 2 of section 17.4 in the next video.